Welcome to the second lecture on Treewidth. If you recall, we stopped last time. So we defined this notion of graph with small separation number, which was basically, let's recall, what was that? A graph had a separation number at most k. If look at any induced subgraph, you can find at most k vertices whose deletion has the property that every connected component has small size. Now, notice that whenever I was trying to make this MIS algorithm, I try to write this recurrence, which you may not even be happy with, is that okay, there are only two sub problems, but in general, if you notice, when I delete one vertex, I could get several components. Maybe each of them has size at most n by 2, right? But like I try to not get into these details of summing over all these components and everything, but let me go through slightly little bit more about this, how you handle if you have several components, to still say that even if you could delete a vertex and every component has size at most n by 2, then we still have a good polynomial time algorithm. Okay. So, let me try to do that for you. So, first of all, I am going to make some assumption or very basic assumption about algorithms, that T of n is greater than equal to T of m if n is greater than equal to m. Okay. So, like they are monotonically increasing functions. That is it. Okay. So, yeah. Okay. So, let us try to understand what I will do, or rather, okay. So, imagine, so let us look at a lemma, and this is nothing, this lemma is about numbers, and this is on purpose I am talking about this number. So, suppose this is about numbers, we have n1, n2, nl, such that ni is at most half of n, and summation of ni, I going from 1 to l is n. Okay. Then I am going to say, then there exists a partition of n1, n2, dot n into a and b, such that, what is the property? Such that summation, rather there exists a partition of 1 to L into A and B, such that summation j into I, A, n j has a property that it is at most n over 3 and at most 2 n over 3, and similarly j and B has a property that n j 2 n over 3. So, what I am saying that if you give me L numbers such that each of them is at most n over 2, their summation is in n, then I can partition these numbers into two parts, okay, so that each part has some threshold, and there is a like threshold from both lower bound and upper bound, and we will see how we can use this. Okay. Okay. So, let's prove this first. It is a very simple fact, and proof is also fairly easy. So, let us arrange these integers in increasing order. Okay. So, suppose we have, like, assume that we have n1, at least n2, at least nl. Okay. So, this is what it is. So, now we have first case, case 1, n1 is less than equal to n over 3. Then Okay. Okay. Or rather, let us say a different case. N1 is greater than or equal to n by 3. This is our first case. If N1 is greater than or equal to n by 3, then I am going to take A equal to 1 and B equal to 2 to L. Let us see why this satisfies the whole thing. Now, notice, so summation, so what is the property in this case? What is the property in this case? What is the sum of N1 is at least n by 3 because of our assumption, and because every number is at most half, it is at most n by 2, which is at most 2n by 3. Okay. Now, look at B, like summation j in B, what is nj, right? Now, notice that nj, because n1 has size at least n over 3, summation of, and so it is definitely at most n minus n1, right, which is at most n1 is at least n over 3. So, this is 2n over 3. Now, what about this? What is summation j in B nj? Well, you are talking about lower bound. Now, you know that n1 has size at most n by 2, right. So, this is definitely again I can say at least n into n minus 1, right. So, I know that summation nj is, so I am going to use the following lower bound, it is n minus n over 2. So, here I use the fact that n1 is at least n by 3 to get an upper bound. I am using here n is at most n by 2 to get a lower bound on this, which is at least n over 2. So, in this case you notice that we have been able to find a partition A and B such that the property is that if I look at the sum of these numbers, they are at least n over 3 and at most n over 2. Okay. Now, what about the case 2? Case 2, so what is the complement of case? So, if n1 is strictly less than n by 3. Okay. Okay. Now, let us say k is the first integer such that, so you are counting like, okay, I am just counting the what is the first integer k such that this number is greater than half. Okay. K is the first integer such that summation j going from 1 to k n1 is greater than or equal to n over 2. Like, what is the first time, what is the first, like, so n1 is the largest number, n2 is a smaller, second largest number, so on and so forth, and say I am going to sum these guys, and the first item k we find that if I look at the summation of first k minus 1, it is strictly less than n by 2, and the moment I add the last item, the kth item, I cross the threshold of this. Okay. Okay. So, meaning the first integer, which basically means that if I look at j to 1 k minus 1 n I n j, okay, this is strictly less than n by 2. Okay. Now, let us try to understand what happens then. So, what can we say about nk? Nk, I know that nk is upper bounded by n over 2. Sure, but this lower upper bound is not useful for my purpose. Why? You will see in a minute. But we can prove something better. Look, n1, which is the largest integer, is at most n over 3. Then the nk, which is smaller than the n1, is going to be at most n3. So, rather than using this, we will use the fact that in fact, look at nk is less than n1, which is less than n over 3. Okay. Okay. So, if that is the case, then Okay, I think I made a mistake. So let me let's not say n by 2. Let's say n over 3. Okay, so okay. Now let's look at my A. So what is A? Is 1 up to k, and B is 1 up to, say, k plus 1 to L. Now let's look at summation I going from 1 to j, or rather, okay. So summation ni or nj, j going from 1 to k minus 1 plus nk. Now what is this? I know this is strictly less than n over 3, right? It is strictly less over than n over 3. And what is nk? Nk is also upper bounded by n over 3. So this is at most 2n by 3. And by choice of k, what do we know? This is definitely, this whole sum is at least n over 3. So again, we are able to prove that the sum of these a's, the integers in index set A, is at least n by 3 and at most 2n by 3. Okay. What about B? Well, let's look at this. So is summation j going from k plus 1 to L n j. What is this? Well, since the sum in A is at least n by 3, right? So it is n minus summation I going from j going from 1 to k n j, which is at least n by 3. So this is at most 2n by 3, because this is at least n by 3, right? It could only be smaller, it cannot be bigger than this. Okay. And now for the lower bound, we will use the same thing, right? I mean, again I can write down this is n minus summation j going from 1 to k n j, right? But what is summation n j upper bounded by? Is 2n by 3. So this will imply n over 3. So once you have the upper bound of n by 3 to n by 3 on A, it automatically actually implies an upper bound for this. Okay. So now with this we are done, because what will I do? Okay. So now in the branching step, suppose let me do it for one, let me do it for single vertex, and then you will understand for others. So suppose I have a vertex V, so that every component had size n by 2. So what will you do? You say, okay, fine. Let us partition these components, partition these components into, say, some, this is A part, and say this is B part. So this is like A, right, based on their sizes, right? And this is B. Right. So I will apply my previous lemma on these numbers. So like suppose this has size n1, n2, n3, blah blah blah. N. So based on the previous lemma, I know that now I can apply the previous lemma with sum being n minus 1, and I can partition this into two parts. Like this is some set of components, B is some set of components, such that what is the property? That here the size of the components, the total size of the components is at most 2n by 3 and at least okay. So this is at most 2n by 3 and at least n over 3, at least n over 3, at most 2n over 3. Okay. So this is the property I have. So now rather than branching on, like rather than making our algorithm work on each component separately, which is the best way to do, just for our analysis we'll say, okay, let's combine these components in A and let's call that left graph, and let's combine the components in the B like in the index set of B, call them a B part. Okay. So now, and I'm going to call my algorithm. So if I delete V, if V is going to be part of the solution, you have to also delete their neighbors. So whatever more components you are going to get after deleting the neighbors of V into A, you are going to call them into one set of one graph, and similarly in the B side. So now what will happen is that you can show that T of n is like you're going to create two problems in each sides. So it is going to be 2 times at most 2n by 3 plus 2 times at most 2n over 3. So, this is like at most 4 times 2 Tn over 3, and you can show that this is n to the power big O of 1. Okay. So, now this time I have not hand waved, right. I have just given you an algorithm with like upper bound running time, which is still polynomial. And so, if it have been, let's say for example, for the k size separator, then you will get something like 2k plus 1, 2 Tn over 3, and in my opinion, this also should be something like n to the power big O of k. So, we are not going to lose anything. Okay. So, this is something which we should know, and we should utilize the fact. Now, having taught you all this, so remember from the last time what we said ourselves, that our question, like 2 questions we asked: is weighted max independent set FPT parameterized by k on class k? On what are the natural families of graphs that has a small separation number? So, let us try to answer the question number 2 first. Okay. Okay. So, here is the question we would like to address. What is the separation number of G if G is a tree on n vertices? Okay. So, notice which basically, if I say, so if we wish to prove that separation number of G is at most k, we should show that for any induced subgraph G, for any induced subgraph G of x on x subset of Vg has a balanced separator of size at most k. This is what we need to show. Okay. Or rather, I have to find a set x of size at most k, or in other words, so that every component has size at most half. Okay. So, this is what we have to show this. So, we will try to show that separation number of a G, and if G is a tree, is at most 1. Okay. Okay. So, to prove this, okay, what I am going to show to you is that rather than proving that separation number of G is at most 1, I am going to prove something more general. Okay. So, what I am going to say, suppose I have been given say tree T, and let us say we have weights, some positive weights, okay, and I am going to define a notion of W balance separator. Okay. So, what is a W balance separator? A set X is called W balanced separator if for each connected component, C of G minus X, we have that weight of C is at most weight of vertex set of G divided by 2. Okay. Now, I am going to show, so this is like a, let us call it a weighted separation number of G. Okay. So, this is the definition of weighted separation number of G. Okay. So, yeah, so we will rather let us leave it for now. Okay. So, I am going to prove to you that for any weight function W, okay, I can find for if, so what I am going to show to you, for any weight function W, a tree T has W balanced separator of size at most 1. Now, okay. Now notice, if we prove this, why are we done? Well, that's very easy, because look at, suppose you wanted to show that X has a balanced separator of size at most, like graph induced on X as a balanced separator of size 1. Then what we need to show? What weight function do we choose? Then we will assign weight, the following weight function we will take. Okay. For V in X, weight of V is 1, and V not in X, weight of V is 0, right? So, notice what happens. So, then if we are able to find a vertex V, and now look at the component, what is the property of this component? Well, what is the weight of this component? Weight of this component is nothing but what is the weight of this component? What is the weight of this component? What is the weight of this component? Weight of this component is nothing but C intersection X. So, suppose some Y is there, right? So, what is the component? It is C intersection X. Because why it is C intersection X? Because those are the only vertices which has some weight. And what is the property of this? Weight of C is at most, weight of C is equal to C intersection X is at most weight of vertex set of G divided by 2, which is at most mod X by 2. Now, if you delete this, right, this set of vertices, right, now, right. So, if I delete this single vertex, whatever that single vertex is, that single vertex could belong to X, could not belong to X, it does not matter, right. If it does not belong to X, then anyway, if you look at the look at the connected component and look at the intersection with X, those are the connected components of X itself, and they all have size at most half. It means basically what was there, that the set X which you gave me already had every connected component has size at most. Graph induced on X, every connected component had size at most half X by 2. Because if it had been connected, then you would have found a vertex from this such that this property holds. Okay. So, if we prove this property for any arbitrary weight function, that given a tree, arbitrary weight function, there exists a weighted balanced separator of size 1, then we have shown that the separation number of this graph is at most 1. Okay. So, let us prove this. Okay. So, here is our theorem. Let T be a tree, W be a weight function, okay, from vertex set to there. Then there exists a vertex V in T, such that for all C of T minus V, weight of C is at most weight of vertex set of T divided by 2. Okay. Proof. What is our proof? You just root the tree at an arbitrary vertex. Okay, root the tree and root the tree at an arbitrary vertex. So, suppose here is a V, here is my tree, okay, and so I am going to ask at each step, is V the desired vertex? Okay, is V the desired vertex? Answer could be yes, Then we are done. Else. We are going to else? No. It means, what is the meaning of this? There exists a component, okay, such that there exists a component such that weight of that component is strictly greater than weight of vertex set of T divided by 2. Okay. So, if I delete V, what are the components? Well, the components are going to be, what are the components? If you delete, this is going to be one component, this is going to be one component, this is going to be the one component. Okay? So, this is going to be one component. So, now, as you have asked yourself, okay, is that, well, if this is not the case, then there is a component here, okay? There is a component here, say this is my component, which is heavy, okay? So, now I am going to ask yourself, okay, fine, let us call that, okay? So, then it is like a think of it, okay, now what I will say, okay, let W be the neighbor of V in C such that weight of C is greater than or equal to weight of vertex. So, now I am going to ask, okay, fine, V is not such a candidate, fine, is here is my W, here. Now, I ask the same question, but okay, I ask the same question, but with W. Ask the same question, but with W. Okay? Now, either we succeed or we fail. If we fail, move to a children of W and so forth. Okay? So, you will keep updating. This is an algorithm actually. Okay? It's an algorithmic proof. But what changes? At each time, the vertex which you are considering, its distance from V increases. So, it's a finite graph. So, after finitely many steps, you will find this vertex, right? Now, why? Because look at is it possible that you reach a leaf and both sides are you understand my question? Right? Because what happens? So, the point is, look at this component, look at the weight of this guy, right? Because this is more than V over 2, weight of this is strictly less than weight of V over 2. So, if you go further, look at the leaf, maybe you can reach a leaf, okay? Why did you reach to this leaf? You reach to this leaf because, well, this is the guy such that whose weight is more than V over 2, right? Because there is no component here, which implies that if you delete this, the component which is left has weight at most V over 2. So, basically, you can show yourself that if you move inductively in this way, you will find a vertex all the time in a tree such that if I delete this, every component has size, the total weight of every component is at most the total weight divided by 2. So, it is not very difficult proof, you can also follow it yourself if I was not very clear in the class. Okay. So, it is great that even for trees, we can find a vertex such that every component has size at most half of this. Now, which implies that the up until now, notice H1 was basically up until now contained paths and more, or sorry, let us call it Z1 graphs with rather, okay. So, G and vertex separation V, separation number of G is at most 1. Okay. So, now what we know? I know that this contains paths. Now, what does it contain? It contains trees, at least this much we know. And if you recall ZK, we know that it contained sub graphs of k times n grids. Okay. In fact, notice what else can it contain? It does not have to be. So, for example, look at this is my right, and this is, suppose this is k cross n by 3 grid, okay, and like this part, and this is another k cross n by 3 grid, and this is another k cross n by 3 grid. So, this is not a grid, like any sub you notice that any sub family, sub graph of even such structure has at most k. So, this is like a tree. So, if you think of this k cross n grid as like a fat path, I have tried to make a fat trees in some sense. Okay. So, even for such objects, these guys will start belonging to the graph ZK. Okay. So, this is what exactly what I. So, now because by proving this nice theorem about trees, okay, we have been able to say to you or show to you that separation in a graph, and separation is very simple property of a graph. What is a simple property? That a graph has a separation number at most k, if for every induced subgraph I can delete k vertices such that every component has size half of what I started with. If this is the case, then the graph has separation number at most k, and for those families of graphs, for those classes of graph, maximum independent set can be solved in n to the power k time. Okay. So, there are lots and lots of graphs where such properties would hold. Okay. You should try to make some examples for yourself. Okay. But the second question that we wanted to resolve or solve last time was the following. Second question. Okay. What about FPT algorithm for say weighted max independent set on graphs? Okay, this is a very basic question we are. Okay, so before we answer this question, okay, before we answer this question, let's try to do this. How can we do these things if for say grid graph? Okay. So, suppose we have, okay, this time I will try to draw right. This is also some subclasses of grids. Okay. Okay. So, this is column 1, column 2, column 3, column 4, column 5, so on and so forth. Maybe, okay, maybe let's try to do it for path itself. Okay. So, we will try to do this a little bit later. Let's do it for path itself. Okay. So, rather than doing divide and conquer, let us exploit more algorithmic. Let us exploit the way these graphs could be constructed for our algorithm, Okay. It will become very clear soon. Okay. So, the idea will be is that, look, suppose somehow I knew, or I am storing some information, okay, storing some information for this graph, say GI, which consists of, say, first I vertices. Okay. Then can I construct, like, store some information for GI helpful in computing max weight. So, from looking at this, I can tell you, hey, oh, this is a max weight independent set. So, I want to store some information. And then the next question is, okay, fine. Can I exploit the fact that, hey, look at the graph between GI and G plus 1. This is like not much. First of all, this is a vertex which only connects to just one vertex of my previous graph GI, and that also with some edge. Can I use this information plus simplicity of going from GI to GI plus 1 to compute my information? Rather, update my information? Okay. So, if I can do this, then from GI plus 1, I will go to GI plus 2, which will use the information stored and the simplicity to get the information. So, there are two things. First of all, what does it mean to be simplicity of this graph? Like how do we construct this simplicity of this graph? That's one thing. Or define such simplicity of graph. And secondly is, what information do I need to store? So, for example, I am going to store the following information. Okay. So, for max independent set, I am going to store information, say AI and BI. Okay. So, what is this? This is going to store okay. This is nothing but max weight independent set in GI, and BI is max weight independent set in GI that does not contain VI. So, basically I am saying, okay, fine, I am going to store two information, because, and from where does this information comes? So, if you look at your divide and conquer algorithm, what are we branching on? We were branching on either my solution contains this independent set, this vertex in the independent set, or it does not. So, in some sense, that is what, rather than doing branching or divide and conquer and then getting those solutions, we are going to store these solutions into a table and going to update this table as and we go forward. Okay. So, let us try to understand. So, now let us look at, suppose I have this information for AI. So, now how we are going to do AI plus 1? What is AI plus? It is a max weight independent set in, so this is what it needs, max weight independent set in GI plus 1. This is what we would like to update. And what is BI plus 1? It is max weight independent set in GI plus 1 that does not contain VI plus 1. Now, what is BI plus 1? Notice. Okay. So, if this is going to be the max weight independent set of GI plus 1 that does not contain VI plus 1, then that must be a max weight independent set of GI, and that we have already stored in AI. So, BI plus 1 is nothing but AI. Good. Okay. So, now what is ai plus 1? Either it contains vi plus 1 or it does not contain vi plus 1. If it contains vi plus 1, then it cannot contain vi also, which implies that that information is nothing but it is a max independent set of gi that does not contain vi, which is stored in B of I. So, ai plus 1 is max. So, if it is going to contain vi plus 1, then it is weight of vi plus 1 plus say B of I. So, this is 1, or it going to contain, or it does not contain vi plus 1, and then we already have updated bi plus 1. So, it is there. Okay. So, we are done, right. So, we are done. So, we have been able to update this information using this. And now, notice this is like a linear time algorithm, right. So, we are just maintaining two cells, right, and go from left to right, and you are able to construct such objects. Okay. Let us ask ourselves, can we do the same thing for the trees? Because here there was a path, there was a notion of left to right, okay. But so we were able to exploit that. How will we exploit such kind of like left to right, right? So, what I mean by left to right? So, there is some way we are constructing this graph, and we are saying, okay, follow this construction of this graph and update your information, right? So, now for trees, what can we do? So, let us look at the tree. So, let us do the same thing with the trees. Let us root the tree at some place, at some node, okay. Let us say W. And now, let us look at a vertex V. Okay. By TV, let us mean tree rooted at V, and BV will be again max weight independent set at max weight independent set in TV that does not contain V. And what is AV? Max weight independent set in TV. Okay. So, same to this, like, so basically this is what. So, notice that because we have rooted this tree, now we do have a notion of where to look. I said, okay, fine, right, fine. So, this is, and we are, what will we do? So, we were doing left to right, but now it is a tree and it is a rooted tree. So, we will do from bottom to top, right. So, first we will take care of leaf, then their parent, and then their parent and their parent. So, okay, left to right replaces bottom to top. Great. So, suppose we are at some vertex V, and here V1, V2, VL, there are L children, okay, there are L children, and now again we will do what is B of V? It is a maximum weight independent set that does not contain V. It means, look at, if it does, then what is the maximum weight independent set that does not contain V? It means it should be maximum in the, it should be maximum in the subtree here, it should be maximum here, it is a maximum here, it is a maximum here, whatever it is. So, B of V is very simple, it is nothing but summation I going from j going from 1 to L, A, B, V, Z, which we have already stored. So, that is great. And now, what is A of V? Okay, fine. You are probably going to contain V in your independent set. If you are going to contain V in the independent set, then you cannot contain V1 to VL. It means in this sub part of the tree, you are looking for a max weight independent set that does not contain V1, but that we have already computed. So, what is A of V is nothing but weight of V plus summation j going from 1 to L, B, V, j. That is correct. or you do not contain V. If you are not going to contain V, then that is like B of V, which we have already computed. So, this is how we can update this information. So, it does not have to have a left to right, but even top to bottom. I noticed that top to bottom generalizes the idea of left to right, because I can think of path also as a tree rooted at Vn and then go from bottom to top. Okay? So, the moment you make Vn as your root, you left to right replaces from bottom to top, and so this idea gets generalized. Okay. Now, so leaves and trees are very beautiful, but now what about this grids or subclasses of grids? So, let us say, never mind if my drawings are not that beautiful. Okay. The way we have constructed path, we could construct this grid as such, like column by column, right. So, first we construct column 1, column 2, column 3, column 4, dot 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 dot, and what will be the graph Gj is basically graph induced on column 1 union dot 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 union column j, right. So, first j graph induced on this. So, I mean, if you really want to make life nicer, maybe like difficult or something, think of them as a subgraph, like some edges are missing, for example. Just it does not matter for our purposes, but like this is missing, or some edges are missing, something. Okay, they are like sub. And we can go from, again as before, we could go from left to right, and whatever we deciding. So, notice what was BBJ storing. BBJ was storing what is the max weight independent set that does not contain some vertex. So, now we will generalize. So, look at the column Cj, okay, and we are going to say, okay, B of x, okay, what is going to be B of x? It is going to store max weight independent set, or maximum weight of an independent set, rather not. Okay, we are going to store max weight independent set in, right. So, you are not going to contain. So, in the graph G j minus x, okay, this is what you are going to store. So, what is the maximum weight independent set in G j minus x? Okay, and that is it. So, look at this. I can find the max weight independent set of my whole graph G by looking at Gn, right, which is nothing but G C1 union Cn column. Okay, and what will I do there? What will I do there here? So, then I know that either the max weight independent set has empty intersection or a non-empty intersection, and based on that we can do everything. Okay. Now, the question is, how are we, so rather than writing this, maybe we can write j comma x is like what is the max weight possible independent set in Gj minus x. Okay. So, let's see how can we Bj x. So, let us try to understand what happens. So, here is a piece of graph for which all these information are there. This part of the graph, and now we have this, say, set x, okay, or no, sorry, Cj, and here is some set x that is not going to be part of the solution. It means the remaining has to be part of your solution. So, what I am saying that what is the max weight possible independent set in Gj minus y. Okay. So, look at the maximum weight independent set, which consists of, that could consist of what? So, notice that could consist of some set here and some set here. Okay. I do not know which set it is, right. So, what generally we do is that we guess, okay, So, we will guess in Cj minus x, let us call that y. So, we guessed that must go to the solution. Okay, that must go to the solution. Okay. So, if this is the y which goes to the solution, what we know? Its neighbors can't go to the solution. And this is where we use the fact that these graphs are constructed very, very, very well, in the sense, where are the neighbors of y? Neighbors of y are either where? In Cj minus 1 or here. This is where the neighbors of these vertices in y are. So, if you pick up y in your solution, you are forbidding which one? You are forbidding all the neighbors of y. So, what is that? So, now I can write down this recurrence. So, the recurrence is, notice, b j x is equal to max y subset of Cj minus x, that is the first. Y is an independent set, otherwise, I mean, you can never complete it to an independent set. And the moment you have this, what is this? So, it is like a weight of y plus. Okay. So, now you know that you are not going to pick anything all as neighbors. So, and you are also know that you are not going to pick anything else from the column Cj. So, everything else is from the induced graph Cj minus 1, and from which you are not going to pick up the n of y. So, basically you are forbidding n of y. So, basically this is nothing but where it is stored. It is stored in b j minus 1 comma n of y intersection Cj minus 1. That is it. So, how much time will it take to fill this table? Notice. Okay. So, choices of y is how much? To fill this table, what is the choices of y? Okay. So, the choices of y is like 2 power k minus cardinality of x, and once we have this, it is like, right. So, we have so many choices, and then you have some 2 power k minus x numbers, and from them you choose the maximum weight. So, to fill this table, it is going to take time to fill table takes 2 power k minus mod x. So, how much overall time does it take to fill? So, it is summation, okay. So, choices of x, right, choices of x, which is like k choose I, right, I going from 0 to k, and for each of them I am going to do this. So, which is nothing but 2 to the power k minus I. Okay. So, by binomial this is going to be some 3 power k and n to the power big of 1. So, actually you can solve all these things in 3 power k running time, which is FPT, right. Now, notice that in all these things we had this notion of graphs, right. So, small graph, then the next we are going to graph, but the interaction between the new set of introduced vertices with the previously constructed graph is limited. So, this is the limit which will help us to construct the definition and the sequence of the graphs we are going to form, and that sequence of the graph is what will allow us to give a decomposition as well as to come up with a dynamic programming algorithm, the one which we have constructed. So, now what we have shown now, okay. So, all we have shown that max independent set is FPT on subclasses of k times n grids, but is max independent set FPT on, we still do not know. Okay. We will take up the thread in the next lecture starting from here.